In this video, we're going to discuss how the matter and radiation in the universe can be modeled as a perfect fluid. We'll talk about how this fluid is at rest with respect to a frame of reference called the cosmic rest frame. Remember, we've been modeling the universe according to the cosmological principle, which postulates that the universe is spatially homogeneous, meaning it looks the same at all points, and spatially isotropic, meaning it looks the same in all directions. In the previous videos, we examined the left side of the Einstein field equations according to the cosmological principle, and this led us to the FLRW metric. In this video, we're going to look at the right side of the Einstein field equations according to the cosmological principle, and we'll see that the energy-momentum tensor represents a fluid with uniform mass density ρ and uniform pressure P. Specifically, we'll look at the case of a perfect fluid, whose energy-momentum tensor with one raised index and one lowered index looks like this, with the energy and pressure on the diagonal and zeros everywhere else. This tensor also represents a perfect fluid in the rest frame of the fluid, and the rest frame of the mass and radiation in the universe is called the cosmic rest frame. So I'm going to cover three topics in this video. First, I'll cover the energy-momentum tensor for a perfect fluid, then I'll explain what the cosmic rest frame is, and finally I'll talk about the equation of state for our perfect fluid. Before we start, let's do a quick review of the energy-momentum tensor, which I'll call the EM tensor for short. We discussed this in more detail in Relativity 107e, but the EM tensor helps us keep track of the total amount of form momentum inside a three-dimensional box in space-time. The alpha-beta component of the energy-momentum tensor counts the flux of alpha momentum going through a unit box at constant beta. For example, if we look at an XYZ box at a constant time, this will give us four components of the EM tensor, where the second index is time. We can count up all the form momentum of the particles and radiation inside, and we'll get four components for the total time, x, y, and z momentum. These give the tt, xt, yt, and zt components of the energy-momentum tensor, respectively. These are basically the densities of form momentum over space. Similarly, if we look at a tyz box at a constant x, this will give us four components of the EM tensor where the second index is x. Counting up all the form momentum components gives us the tx, xx, yx, and zx components of the EM tensor. These are basically the current densities or fluxes of form momentum along the x direction. And we get similar results for a txz box at a constant y and a txy box at a constant z. Recall, the time component of form momentum is just energy, and the flux across a box of constant time is just density, since that's just counting the number of something in a spatial box at a constant time. We can identify the components of the EM tensor as energy density, energy flux, momentum density, and momentum flux. The momentum flux can be broken up into pressure, where the momentum is perpendicular to a surface, and shear stress, where the momentum is parallel to the surface. Also, the EM tensor is symmetric, so we can swap the indices without changing the value. So, given that review, we're ready to describe our spatially homogeneous and isotropic universe as a perfect fluid, which is a fluid that exerts pressure equally in all directions. In flat space-time, the perfect fluid EM tensor looks like this, with equal pressure in all directions, and an energy density given by mass density ρ times c squared. This is like E equals mc squared, but divided by volume to write the energy density as the mass density times c squared. All other components are zero because perfect fluids have no shear stresses or viscosity. So this is the energy-momentum tensor for a perfect fluid in the flat space-time of special relativity. And I should also mention that the components you see here in this matrix are measured relative to the rest frame of the fluid. So it's measured in a reference frame where the fluid is stationary and not traveling through space. Now let's try and find the equivalent perfect fluid energy momentum tensor for the curved spacetime of general relativity. First, we can take the matrix and write it as a sum of two matrices. The first has energy density plus pressure in the top left entry, and the second has pressure along the main diagonal. But the first entry has negative pressure to cancel out the positive pressure that we added in the first matrix. Then we factor out rho plus p over c squared from the first matrix, and leave c squared in the first entry. Then we factor p from the second matrix. The first matrix can now be written as the outer product of a column vector and a row vector, each with c in the first entry and zeros everywhere else. I'm also going to factor a -1 from the second matrix to flip all the signs in it. Now, if you recall, the components of the 4-velocity vector are given in this column multiplied by the gamma factor. But if we look at the 4-velocity vector for a particle at rest with 0 velocity, this particle has a gamma factor of 1, and so the resulting components look like this. So these two vectors are really the 4-velocity vectors for a particle that's at rest, moving through time but not moving in space. So for a flat space-time, we can write the perfect fluid energy momentum tensor in abstract notation like this, where these become the tensor product of 4-velocity vectors, and this becomes the flat Minkowski metric eta. Also note that we're using the mostly minus metric convention, so we use a minus sign in this equation. If we're using the mostly plus metric convention, this sign becomes a plus sign instead. To get the equivalent version of a perfect fluid EM tensor for curved spacetime, we just take the flat metric eta and replace it with a general metric g. So this is the abstract formula for the EM tensor of a perfect fluid. But if we choose a basis, we can write the tensor as a linear combination of this basis. And so we get the components of the EM tensor, the components of the 4 velocities, and the components of the inverse metric, since we're dealing with upper indices. So this is the EM tensor for a perfect fluid with upper indices. But we can also get a version with one upper and one lower index, if we lower one of the indices using a summation with the metric. This will lower one of the 4-velocity indices, and this inverse metric and metric cancel to give a Kronecker delta, or identity matrix. To get the EM tensor with lowered indices, we can sum with another metric. This lowers the other 4-velocity index, and the identity matrix times the metric just gives the metric. Now, for our universe obeying the cosmological principle, we use the FLRW metric, as discussed in Relativity 110b and 110c. The 4-velocity vector with lowered indices equals the ordinary 4-velocity summed with the metric, which looks like this if we expand the summation. Let's look at the special case of the U0 component. For the FLRW metric, G00 equals +1, but all these other metric components go to 0. So for the FLRW metric, U0 with a lowered index equals U0 with an upper index. So looking at all these different EM tensors, for the FLRW metric in the rest frame of the fluid, U0 lower and U0 upper are both equal to c, and the spatial components are all 0. So if we look at the EM tensor with one upper and one lower index, also called mixed indices, in the rest frame, both U vectors look like this, and the identity matrix looks like this. So we can multiply these, distribute, and then add the matrices together to get this result. For the EM tensor with upper indices, we get a similar formula, except we use the inverse FLRW metric, where the 0,0 component is +1, as we said before. But the spatial components are more complicated, so I'm just going to write them as GIJ with upper indices. So the final result looks like this. And for the EM tensor with lower indices, it looks the exact same, except with the ordinary metric with lower indices instead. So these are all the various perfect fluid energy momentum tensors in the rest frame coordinates of the fluid for the FLRW metric, using the mostly minus metric signature. Now, I'd like to bring up a couple concerns. So we know that this energy momentum tensor represents the matter and radiation in the universe as a fluid that's at rest. But with respect to which frame is the fluid at rest? In special and general relativity, there should be no objective frame that's at rest, since all inertial frames should be equivalent to each other. So it would make sense to talk about a fluid that's at rest inside a cup, because we could just use the rest frame of the cup. But here we're talking about the whole universe. So how could the whole universe have a rest frame? The next concern is this FLRW metric that we've been talking about. The metric has the spatial scaling factor A of t, but which reference frame does the time coordinate t in A of t belong to? In special and general relativity, there should be no objective t-coordinate, since every frame of reference will have its own t-coordinate. So whose time coordinate is this? Both of these concerns with the rest frame of the EM tensor and the scale factor's time coordinate can be answered at the same time. It turns out that all the matter in the universe does actually have a rest frame called the cosmic rest frame. In the Relativity 110a video, I talked about how, if we look up at the sky from different parts of the Earth, we'll measure the cosmic microwave background radiation coming at us from all directions. In half of the sky, the CMB radiation will be more redshifted, and in the other half of the sky, the radiation will be more blue-shifted. Basically, since the Earth is traveling through an ocean of CMB radiation, the radiation will be more redshifted on the half of the sky that the Earth is traveling away from, and the radiation will be more blue-shifted on the half of the sky that the Earth is traveling toward. Now, most frames of reference for all these stars and planets in the universe will have the CMB radiation Doppler shifted along one direction or another. But there is one specific frame where the CMB radiation has no Doppler shift. The frame of reference where this happens is called the cosmic rest frame. The cosmic rest frame is the unique frame of reference where there is no observed Doppler shift in the CMB radiation, and the CMB radiation's frequencies look the same in all directions. This is also the frame where, if we zoom out on large scales and divide the universe up into boxes hundreds of millions of light years wide, then the average velocity of all the masses inside these boxes will be 0. Basically, inside these boxes, there will be planets and stars traveling in all sorts of directions, but if we average over all the masses in the box, the velocities will all cancel out with each other and will average to 0. Now, hearing about the cosmic rest frame, you might get the feeling that it's not any different than the ether reference frame that was proposed in the late 1800s. But the cosmic rest frame and the ether are not the same thing. The reason that physicists proposed the ether is that Maxwell's equations predicted that light waves had a speed of 300 million meters per second in a vacuum. But the equations didn't specify which frame this speed was measured relative to. The ether was proposed as a special reference frame that light travels in, and Maxwell's equations would only work when calculated relative to the ether frame. Special and general relativity reject the existence of the ether. Special and general relativity claim that all laws of physics, including the speed of light c and Maxwell's equations, are the same in all frames of reference, although special relativity ignores the laws of gravity. In these relativity theories, the equations describing the laws of physics are the same in every single frame, whether the frames are inertial or non-inertial. As long as we write the laws of physics using invariant four-dimensional tensors, the equations describing the laws of physics will be the same in all frames. So the cosmic rest frame in general relativity has nothing to do with the laws of physics working or not working in special frames. The cosmic rest frame is really about the distribution of radiation and matter in our universe. If you fly around in space in a rocket, in most frames, the CMB radiation will have a Doppler shift. But there's one specific frame where you'll see no Doppler shift in the CMB radiation. In this frame, you are basically at rest with respect to the ocean of CMB radiation. This is the frame in which we plan to measure the components of our energy momentum tensor for the perfect fluid that describes the matter and radiation in our universe. When we observe the universe from the cosmic rest frame, we will get three-dimensional spatial slices of space-time. And these three-dimensional spatial slices can be defined by the r, theta, and phi space coordinates used in the FLRW co-moving coordinates. And the space-time direction that's orthogonal to these spatial slices defines the time coordinate t for the scale factor a of t. So the t in a of t is the time coordinate of the cosmic rest frame. So to conclude this section of the video, in a universe that's changing in spatial scale, like ours, there is a choice of frame at every spatial point where there is no observed Doppler shift in the CMB radiation, and the average velocity of matter at large scales is 0. Collectively, all these frames at all these spatial points in the universe are called the cosmic rest frame. This is the frame that comes from the distribution of matter and radiation in the universe. The laws of physics are still the same in every frame, as expected in special and general relativity. But the cosmic rest frame lets us define motion relative to the cosmic microwave background radiation. Now, you might wonder, what if the universe was empty? How would we define the cosmic rest frame then? And it turns out that you can't. In this case, all of space-time becomes homogeneous and isotropic, not just the spatial slices. An empty universe with zero curvature is Minkowski space, the flat space-time from special relativity. An empty universe with positive curvature is called de Sitter space, and an empty universe with negative curvature is called anti-de Sitter space. These are the space-time versions of flat space, spherical space, and hyperbolic space. We'll cover them in more detail in the next video when we see how the Friedmann equations define the evolution of the universe over time. The last thing I'll talk about in this video is called the equation of state for the universe. The idea of an equation of state comes from thermodynamics and chemistry, where we relate variables that describe the state of a system, like pressure, volume, density, and temperature, together in an equation. The most famous equation of state is the ideal gas law, which relates pressure, volume, temperature, and the number of moles of the gas. We're going to need an equation of state that relates the energy density and pressure of the perfect fluid we're using to model the matter and radiation in our universe. Now, there are any number of different equations of state we could come up with, relating density, pressure, and temperature. But as a first step, we're just going to choose the simplest thing possible and set the energy density to be proportional to the pressure, with a constant of proportionality W. So according to this equation of state, if density goes up, pressure goes up, and if density goes down, pressure goes down. This might not be the most accurate equation of state for the universe, but generally speaking, it's good to start with something simple and then improve it later on if it gives us bad results. Using language from the study of fluids, we're assuming our perfect fluid is a barotropic fluid, which means a fluid whose density only depends on pressure and no other state variables. Now let's look at how the value of W affects our energy momentum tensor. If we set W to 0, this means the pressure is set to 0, and we're only left with mass density. This gives us an energy momentum tensor for dust, which is suitable for describing massive matter that doesn't exert any pressure. What if we wanted to describe radiation instead of matter? Well, the energy momentum tensor for pure electromagnetic radiation looks like this, where F is the Faraday tensor. This looks complicated, but if we take the trace of this tensor, we find that all the terms cancel and we get 0. So the energy momentum tensor for pure radiation has 0 trace. Given our perfect fluid energy momentum tensor, its trace is the energy density minus 3 times the pressure. So the only way to set this to 0 is if energy density equals 1/3 of the pressure. So the equation of state for pure radiation involves a W factor of 1/3 between energy density and radiation. One last case to try is setting W to -1. Here, pressure equals negative energy density, so we end up getting an energy momentum tensor with mixed indices that's just the energy density times the identity matrix. And we can lower the indices with a metric tensor and get this. Now, notice that this energy momentum tensor is just a constant times the metric. And that's exactly what the cosmological constant term looks like in the Einstein field equations. If we replace the cosmological constant term with an energy density term and bring it over to the other side, it looks exactly like an energy momentum tensor where the equation of state parameter W is -1. For this reason, the cosmological constant is said to be like an energy momentum tensor with negative pressure. We'll see how this causes the universe's expansion to accelerate outward in the next video. So to summarize this video, we learned about the energy momentum tensor for a perfect fluid, whose components in the various forms look like this. We also learned about the cosmic rest frame, which is a frame of reference where no Doppler shift is observed in the CMB radiation, and where the average velocity of matter at large scales is 0. This is the rest frame in which we measure the components of our perfect fluid energy momentum tensor for the Einstein field equations. It's also the frame where our scaling factor A of t from the FLRW metric applies. Finally, we talked about an equation of state for our perfect fluid. We chose the simplest equation of state, where the energy density is proportional to the pressure using a factor W. W equals 0 corresponds to dust-like matter. W equals 1/3 corresponds to radiation. And W equals -1 corresponds to a cosmological constant-like term, or dark energy. In the next video, we'll use everything we've learned so far to derive the Friedmann equations, and look at the various types of universe evolutions they predict.